case somebody's missing, I'll take a video. So I think, first of all, I should talk to you guys just a little bit about exponential function. We've talked about sine, cosine, polynomials, the usual suspects, right? But one of the things that slipped through the cracks, just didn't happen yet, was the exponential function. So the exponential function, f of x equals e to the x, it's a very special function. The number e we can define as the real number for which the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. All right? You can see that such a number exists if you study like 2 to the power x and 3 to the power x. If you look at the slope of the tangent line to the y equals 2 to the x function, the y equals 3 to the x function, you can see numerically that those slopes have to be between, they're above and below 1. So it stands to reason that there's some number between 2 and 3 which has slope 1 as you cross the y-axis for the exponential function. And that function in particular is e to the x. And so here's the proof of the derivative rule. The derivative with respect to x of e to the x. We do the difference quotient, right? Laws of exponents, e to the x plus h is e to the x times e to the h. So then I can factor out e to the x like that. I'm left with this, but this number by definition, this limit by definition is 1. So there you go. The derivative of the exponential function is the exponential function. You can, in some sense, actually, that you could take that as a definition of e. E is the number for which the function has the same slope as its derivative. The value of the function is equal to the slope of the function at each point. That's what the exponential function is. It's another way you could define e to be that number. But anyway, that's the number. That's the definition in my notes for the moment. So we'll go with that. So again, and we need this for today's lab because our example is using the exponential function. So here you go. All right? That one's pretty easy. Then the other thing that I need to talk to you guys a little bit about is just what is Newton's method. All right? So the basic problem of Newton's method is, here's the goal. Solve f of x equals to 0. All right? That's the goal of Newton's method, is to solve f of x equals to 0. And so, in particular, we could look at this graphically. So I'm going to try to illustrate the method with a sort of heuristic picture. Something like this, let's say. Right, and so maybe I'm a really bad guesser. So as you can see, the answer right here is what we'd call x star. That's the actual root. F of x star is what? Would be 0, right? We're trying to find that 0. And so what Newton's method says is, for whatever reason you can't actually do that algebraically, you make a guess. Let's say here. Our initial guess we call x sub 0. All right? And so we guess x sub 0. But you calculate f of x sub 0, and it's not equal to 0, right? As you can see up here, it's not equal to 0. All right? And then what Newton's method says is, okay, well, I can't, that doesn't work. So what I'm going to do is I'm going to take the function, and instead of looking at the function, I'm going to look at its tangent line at that point. See that? The tangent line at that point. And right here, I'm going to find out what that is. I'm going to find out where the tangent line has a 0. So what's the equation of that tangent line? Y equals what? It's equal to f of x naught plus f prime of x naught times x minus x naught, right? That's the equation of the tangent line that goes through this point right here, as we've discussed. So my question for you is, can you work out what this specific point is right here? We're going to call that x1. What's x1 equal to? negative something. Let's see here if I can. How about this? We do the algebra. So we're setting 0 equal to f of x naught, whatever that is, all right, plus f prime of x naught times x1 minus x naught, right? We need to solve that equation for x1. So we can do that, right? Like subtract f of x naught to the other side, divide by the derivative. We get x1 minus x naught equals to minus f of x naught divided by the derivative at x naught, like that, right? And then, hey, check it out. So there's the formula. x1 equals to x sub 0 minus the value of the function at x naught divided by the derivative at x naught. So that formula I just boxed there, that's the first, that's the first iteration in Newton's method, right? So, and then you do what? You say, okay, well now I'm going to check f of x1. What do I get? Well, if I got 0, I'm done, right? But if I don't get 0, what do I do? Well, I look at the graph. Okay, so f of x1 is here, you know? This right here, this point, is x1 comma f of x1, right? And next up, I do the tangent line again. Like that, right? And that's going to define another point, which we'll call x2. x2 is where the tangent line to the function at x1 crosses the x-axis, right? What's the formula for x2? By the same math, with x1 playing the role x0 did and x2 playing the role x1 did, the same mathematics gives us that x2 is equal to x1 minus f of x1 over f prime of x1. That's x2, right? And then you check f of x2, you know? It's not 0, right? And you look at the tangent line to x2. That brings you to x3, right? And you look for its x-intercept, that tangent line. Well, x3 is the interception of the third tangent line, which was based at x2. Then that gets you this point up here. And then you look at the tangent line at x3 comma f of x3. Right? And what's happening? Look, right, it's getting us closer and closer to what? To the answer, which was right here. So this is Newton's method. You make a guess, and then you follow the following rule. X sub n is equal to x sub, well, I'll use n plus 1. X sub n plus 1 is equal to x sub n minus f of xn over f prime of xn. This is Newton's method. Now, it doesn't always work, all right? But it's one of the standard numerical techniques for solving an equation, right? Instead of solving the equation directly, you find its linearization and solve that, and then just kind of iterate. So that, in a nutshell, is Newton's method, and so that's what the lab today is based on. The other thing it's based on is we're going to use Excel today to do the calculations. So if we do it right, we're going to be able to like cut and paste from Excel into the lab document. But at the start of the lab, I still have you use Wolfram Alpha, but in the later part of the lab, we'll use Excel, so you should go faster. So I'll shut up and let you guys get to work. I'll try to help you individually from this point here. So thanks, everybody.